Today we're looking at 4.5, which is modeling with exponential and logarithmic functions. So we'll look at just a few models here. So the first one of the most common ones, is the exponential growth model. And it says a population that experiences exponential growth increases according to the model n of t equals n sub 0 times e to the rt. So n sub 0 is just your starting amount. So it says n of t is your population at time t. N sub 0 is the initial size of the population. R is the relative rate of growth, and this is says expressed as a proportion of the population, and then t is time. So that's what each variable means. And we'll do our first example right here. So it's predicting the size of a population. So it says the initial bacterium count in a culture is 500. A biologist later makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. Find a function that models the number of bacteria after t hours. So we're going to use that model n of t equals n sub 0 e to the rt. And we just have to fill in stuff for n sub 0, r, and t. Or I'm sorry, n sub 0 and r to create a model. It says find a function that models it. All right, so what is the initial count? Well, it tells you the initial count is 500. So n sub 0 is 500. And what else do we need? So we're going to have e and the rate. It says the rate of growth is 40%. So we convert that to a decimal and then put it in the exponent. So 0.4 t. So your growth model right there is 500 e to the 0.4 t. And then it says, so we just did the a part, what is the estimated count after 10 hours? Well, that's just n of 10. Okay. And then if you calculate that out with the calculator, it's approximately 27,300. And this is bacteria. Okay, so that's one of the most straightforward examples you could do. Just find the function and check a value in it. Okay, so let's do this example. It says finding the initial population. So it says a certain breed of rabbit was introduced onto a small island about 8 years ago. The current rabbit population on the island is estimated to be 4,100, with a relative growth rate of 55% per year. What is the initial size of the rabbit population? So once again, we're using this model. N of t equals n sub 0 e to the rt. I always call this one NERT. And we're solving now for the initial size of the population. So we don't know n sub 0, but we do know that the current population is 4,100. So if we plugged in the initial, calculated it out, we would get 4,100. And then it says the relative growth rate is 55% per year. So that would be 0.55. And it says 8 years ago, this population was introduced to this island, so this t would be 8. So in this case, you can see we're going to solve for n sub 0, which is fairly easy in this case. We just divide by e to the 0.55 times 8. So I'll divide both sides by e to the 0.55 times 8. Generally, I won't calculate these out till the very last step because I don't want to estimate twice, and I don't need to do that. So n sub 0 equals 4,100 divided by e raised to the 0.55 times 8. And if you calculate this out, it's approximately 50. So 50 rabbits. Okay, so 50 rabbits. Now that would be A. Let's look at B. It says estimate the population 12 years from now. Well, we have the model. I'll just write the model out. So it would be n of t equals 50 times e to the 0.55t. So that would be our model that we'd use. And then we just calculate n of, let's see, it says 12 years from now. So the rabbit population started out 8 years ago at 50. So this would be n of 12 plus 8, so 20. So we'd have 50 times e to the 0.55 times 20. And these are calculator problems, and then we estimate. So this would be approximately 2,993,707. And this is rabbits. Okay, so that is a pretty standard example. That feels a lot more like the homework. Okay, so we have now the radioactive decay model. Now this one looks very much like the exponential growth model, except it's decay. So there's really only one difference aside from the m, instead of an n, but it's just this negative r in there. So it says if m sub 0 is the initial mass of a radioactive substance with half-life h, then the mass remaining at time t is modeled by the function m of t equals m sub 0 times e raised to the negative rt. And then you'll notice it defines r right here. We get r by taking the natural log of 2 and dividing it by the half-life. So we'll use that in this example. So let's do the first example with radioactive decay, and I'll try to keep that on the screen. Actually, I'm going to rewrite those down here so I can have more room. So m sub 0, m sub 0 times e to the negative rt. That would be the general growth model, and then r is defined as natural log of 2 over h. Okay, so it says polonium-210 has a half-life of 140 days. Suppose a sample of this substance has a mass of 300 milligrams. Find a function that models the amount of the sample remaining at time t. Okay, so for this one, again, we're using this model. So m of t, this would be a. It says that the initial mass is 300. And this would be E. And then we don't have R, but it does tell us the half-life. So we'd first find the half-life over here. So, or not the half-life, we'd find R by using the natural log of 2 divided by the half-life of 140. And if you calculate that out, it is approximately 0.00495. So this is our rate. So then when I put it in the function, I'm going to put it as a negative 0.00495, and then we attach our t up there. So our model is m of t equals 300 times e raised to the negative 0.00495t. For the B part, it says find the mass remaining after 1 year. Notice that the half-life was given in days, so we would have to convert the year to days. So we're going to use 365 instead of 1. So it says find the mass remaining after 1 year. Let's go ahead and do that. So this would be m of 365 equals 300 times e raised to the negative 0.00495 times 365. And after that, we get, let's see, it's approximately 49.256. And this would be milligrams. Okay, so let's go through the last little part. And most of the questions follow a similar format. You're solving for, T, R, or initial population in the for most of the examples. So it says, how long will it take for the sample to decay to a mass of 200 milligrams? So it's asking for how long, so we're solving for T in this case. So we'd have 200 equals 300 times e raised to the negative 0.00495 t. And now we're going to use some logarithmic properties. So we're solving for t. We need to get that down to the front of this equation. So we're going to divide everything by 300, try to isolate the t. So on the left, 200 over 300 becomes 2 over 3. And once you get a feel for these, you will probably skip some of the steps that I'm going to go through here because they become really obvious every time. Okay, so now I need to bring the t down to the front, and I can do that by using a logarithm. So natural log of 2/3 equals the natural log of e raised to the negative 0.00. Okay, so notice I used the natural log as opposed to log log, and that's because this is, I see e's, so I want to be able to, cancel those out as quickly as possible. So anyway, on the right side, we get negative 0.00495 t times the natural log of e. And on the right, it's natural log of 2 over 3. All right, so on the right side of the equation, we have a natural log of e, so that is just 1. So this equals 1, so we don't really have to worry about that. In the last step, we divide. So t would be equal to the natural log of 2/3 divided by negative 0.00495. And so if I were to calculate that out, that comes out to around 81.9. And so that's days. So just keep in mind that with decay functions, when we're using radioactive decay, the larger number that you plug in, the the answer should be less than your initial. Okay, Newton's law of cooling. So there are actually more formulas in this section than what we're doing, but we're focusing just on a few of them. So I'll read this. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that the temperature difference is not too large. Using calculus, the following model can be deduced from this law. And so then in the blue box, we have the law. So if D sub 0 is the initial temperature difference, that's a key part, between the object and its surroundings, and if its surroundings have temperature T sub s, then the temperature of the object at time t is modeled by the function T of t equals T sub s plus D sub 0 times e to the negative kt. All right, so if you really look at this and you want to find similarities, this law, if you look at this part, so we have T sub s plus D sub 0 e to the negative kt. That D sub 0 e to the negative kt is basically the radioactive decay. We're using that same principle. So just using a different variable in front. and a K instead of an R, but it is all derived from that same place. And K is a positive constant that depends on the type of object. Okay, so this one we focus less on, but I thought I'd throw it in here. So it says a cup of coffee has a temperature of 200 degrees Fahrenheit and is placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. Find a function that models the temperature of the coffee at time t. So in that, it says the temperature of the room is 70 degrees. So the temperature difference, so I have to do that first, is going to be the difference between the temperature of the coffee subtracting, so 70, which is the temperature of the room. So D sub 0 is 130. And that's, degrees Fahrenheit. Okay, so we have that. The temperature of the surroundings are 70, so let's look at the formula. So capital T of lowercase t equals 70 plus 130, and then it's E to the negative kt. So right now, that's what we have. So that's not our model completely. We would still need to find k. Okay, so in this example, it gives us this information. It says after 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. So we're going to use that to fill in for the variable t to solve for k and then find the model. So it's not like a totally linear process to find these. Sometimes you have to find a lot of other things before you find the model. So I will use that fact. So it's what that's telling me, after 10 minutes, the temperature of the coffee is 150 degrees, tells me that capital T of 10 equals 150. Okay, so if I plug in a 10, I'll get a 150 out. So this would look like 150 equals 70 plus 130 times e raised to the negative k times 10. So now our job is to solve for that k. So let's subtract 70 to get, so this would be 80 equals 130 e to the negative 10k. And then we just keep going with this. So if I divide by 80, I'm sorry, not divide by 80, we're going to divide by 130. So then we get 80 over 130, that's going to simplify to 8 over 13 equals e to the negative 10k. And this looks, at this point, just like the last problem when we were solving for time in that one. So now I'm going to take the natural log of both sides. So the natural log of 8 over 13 equals the natural log. I'm going to shorten this process. So I'm going to bring the 10k down now. And this is the natural log of e. And since the natural log of e is equal to 1, I'll just get rid of it. So I don't have to do that and write that again. And then divide. So k equals the natural log of 8 over 13 divided by negative 10, which is approximately 0.04855. And these numbers that I'm getting are all coming from a calculator, obviously. Okay, so we have k is approximately that decimal. So for this a part, we're still not done, but now we just plug everything in. So I'll write it here. So our formula or model is t, so capital T of lowercase t equals 70 plus 130 raised to the negative 0.04855t. Oh, I forgot my e. Let me scoot that back. 130 times e raised to that. So that is our model, and we just completed A in that question. So let's look at B. B should be shorter. It says find the temperature of the coffee after 15 minutes. So now we're using it. So T of 15 equals 70 plus 130 e to the negative 0.04855 times 15. So using the model is always the easiest part. And that is approximately 130 degrees Fahrenheit. Okay, so for this last part, the C part, it says, when will the coffee have cooled to 100 degrees Fahrenheit? You'll notice I cleaned the page up a little bit. So let's do that one. So now it's asking us, it says when, so now we're going to be solving for T. So it's saying the coffee has cooled to 100, so 100 equals 70 plus 130 e to the negative 0.04855 T, and we want that T. So subtract 70 from both sides to get 30 equals 130 e to the negative 0.04855 T. And you'll notice from this point on, almost all of these questions, and in your homework it's the same. You start completing the exact same process. So we divide by 130 in this case. 330 over 130 is 3 over 13 equals e to the negative 0.04855 T. Take the natural log. So these are all the steps that repeat in every question. So this would be negative 0.04855, and I am skipping that step of writing natural log, then bringing it down. I'm doing it in one step. And then again, this natural log of e here is equal to 1. So I'm going to just clear it up there. And now T equals the natural log of 3 over 13 divided by negative 0.04855. And then calculate. So this is approximately 30.2 minutes. So it'll take 30.2 minutes for the coffee to cool from its initial state to 100 degrees, or initial temperature. Okay, so this will be the last example. This one is pulled from the problem set. Just thought I'd work through one of those as well. So it says the frog population is a small pond. No, the frog population in a small pond grows exponentially. The current population is 85 frogs, and the relative growth rate is 18% per year. Find a function that models the population after T years. Okay. So first of all, we're using an exponential growth model. So this would be, I wrote an n, but you can actually, it doesn't really matter. N of t equals n sub 0 e to the rt is our growth expression. So we're going to find that model. So what's the initial population? 85. So this will be n of t equals 85 e, and then we just plug in the rate. It's 18%. So 0.18 times t. So that would be our first step in that one. So pretty easy one to set up. And then it says find the projected population after 3 years. Again, this is pretty straightforward. N of 3. So 85e raised to the 0.18 times 3. And let's not put an approximately because we should have whole frogs. So if I plug that in, it's 146. It is an approximation, but I think we're rounding up. Can't remember when I calculated that, what I did, if I rounded up or down, but I think I rounded up. Now, C says find the number of years required for the frog population to reach 600. So what we do for C, we say 600 equals 85 times e to the 0.18 times t. So we're looking for t, it's in years. So just like all of the other ones, we say we divide out the 85. So on the left, we have 600 divided by 85, which is going to be 120 over 17, equals e to the 0.18t. And now again, this is that repetition of take the natural log, bring the exponent down, and divide. So we would take the natural log of 120 over 17 equals 0.18t times the natural log of e. The natural log of e is 1, so I can say, okay, calculated. Now we divide. So t is the natural log of 120 over 17 divided by 0.18, and that comes out to approximately that's approximately 10.86, and that is years.